Hi, I'm Matt, and in this video we're going to go over how to evaluate a limit when evaluation of that limit involves an indeterminate form. So first off, what is an indeterminate or an indeterminate form? And when a limit cannot be evaluated by directly plugging in a value, we say that the result is indeterminate, and that just means it's still a mystery. We don't know what it is. The value of that limit is unknown. Now, it's important to differentiate this from the limit being undefined or not existing. Because when we say it's undefined or doesn't exist, that means no matter what we do, we will never find this limit. Because again, the limit does not exist. And indeterminate just means we can't know what the limit is by the mathematical steps we've taken so far. So there are 7 common types of indeterminate forms that I've listed here. They are 0 over 0, 0 times infinity, infinity divided by infinity, infinity minus infinity, infinity to the 0th, 0 to the 0 power, and 1 to the infinity power. The one we're going to talk about most in this video is 0 over 0 here. And that's because when we have 0 over 0, that's indicative of there being a hole on a graph. And we know if you've watched my video on evaluating limits from graphs, that when there's a hole, the limit will typically exist. So now, how do we evaluate the limit as x approaches a of f of x? So if you watched my introduction to limit video, we talked about what to do with it piecewise. And if you watched my last video, we saw that when we evaluate the function at x equals a, we can get a real number. This video, we're now going to look at the second possible case, and that's that we obtain one of these indeterminate forms. So what do we do when we get an indeterminate? We're going to simplify the function in some way to remove that indeterminate, and then we're going to go back up here to then plugging in the value of x of a again. But we see this is a cyclic process. So let's say we evaluate it, we get an indeterminate, we simplify it, and we get back here. We could still get another indeterminate. That means whatever we tried didn't work, and then we would continue this again. There's the other possibility that we get a real number after we evaluate it at x equals a, or after we remove an indeterminate, we could even get this third case that I will discuss in a future video. But again, this process of removing an indeterminate is cyclic, and eventually we get back to direct evaluation. So now let's actually discuss the steps we're going to use to evaluate the limit when there's an indeterminate form. So the first 2 steps are mostly the same as my previous video. We're always going to write the function first, and then we're going to plug in the value of a and show that it evaluates to an indeterminate this time. Note that this is mandatory. We have to show that it evaluates to an indeterminate before we start doing any amount of manipulation. Next, once we have the indeterminate form, we're going to want to simplify our expression in some way. If we have a polynomial, this will typically involve factoring the polynomial, and if we have some form of radical, we're going to often use the conjugate to simplify. These are not the only methods of simplifying, but they are by far the most common way that I have seen. And once we simplify the expression in a way that hopefully removes the determinant, we're going to then plug in that value of a again. And in this video, that will always give us a real number, but in reality, we could get a real number, another indeterminate, and we go through that cycle I showed previously, or we're going to get the third case that I haven't discussed yet, and I'm not going to discuss in this video. And once we do that and we find the value of the limit, then the last step is just to write the answer in the proper form, that the limit as x approaches a of f of x is equal to L. So now let's try an example. So for our first example, we're going to evaluate the limit as x approaches 4 of x squared minus 16 divided by x minus 4. So the first thing we're going to do is write our function x squared minus 16 over x minus 4. And then we're going to evaluate it when x equals 4. Doing so gives us 4 squared minus 16 over 4 minus 4. And this, valuing the numerator and the denominator, gives us 0 over 0. So, as is necessary in step 2, we have now shown that this is an indeterminate. We'll now move on to manipulating the function. So again, we have x squared minus 16 divided by x minus 4. The numerator is the difference of 2 perfect squares, so it could be factored into x minus 4 and x plus 4. And now we see that we have an x minus 4 in the numerator and the denominator. So we could cross out the x minus 4 from both and get x plus 4. However, since we crossed out an x minus 4 in the denominator, we need to note that this function is only equal to x plus 4 when x does not equal 4. Because if x does equal 4, again, we get that indeterminate or a hole in our graph. So now that we've simplified our function, we know that these limits are going to be equal since the limit is unaffected by the presence of holes. So we have the limit as x approaches 4 of x squared minus 16 over x minus 4 is equal to the limit as x approaches 4 of x plus 4. Therefore, we can plug in our function now and go back to step 4 of our list. So we're going to again write the function and then evaluate it when x equals 4. Doing so gives us 4 plus 4, or 8. So now we're at step 5. We just need to write our final answer that the limit as x approaches 4 of x squared minus 16 over x minus 4 is equal to 8. And that is our final answer. Now, real quick, if we were to look at this function on a graph, what we would find is, just give me one sec. Let's say this is 4, and up here is 8. We would get that our graph would look like this. So again, now we could also look at this limit graphically and see that from the left and the right, we would be approaching 8. For our next example, we're going to look at the limit as x approaches negative 2 of x cubed plus 8 divided by x plus 2. So the first thing we're going to want to do, as usual, is write our function x cubed plus 8 over x plus 2. And then we're going to evaluate it as x equals negative 2. Doing so gives negative 2 cubed plus 8 over negative 2 plus 2. And this just evaluates to a 0 divided by a 0. So we have now shown that the initial evaluation yields an indeterminate. We have finished step 2. We're going to move on to step 3 and see how we can simplify this function. So the way we're going to go for simplifying is again factoring, since the numerator is a polynomial. So we're going to factor the cubic in the numerator using the sum of perfect cubes rule, which gives us here that x plus 2 times x squared minus 2x plus 4 is equal to x cubed plus 8. Note that since we have a positive here, our first term is going to be positive and our second is negative. And then remember that the last term, regardless of it's the sum or the difference of perfect cubes, will always be positive. Sorry. So now we could write our denominator, and we realize that we could cross out an x plus 2 in both. And we get that x cubed plus 8 divided by x plus 2 is equal to x squared minus 2x plus 4, so long as x does not equal negative 2. And now we're going to say that the limit as x approaches negative 2 of x cubed plus 8 over x plus 2 is going to be equal to the limit as x approaches negative 2 of x squared minus 2x plus 4. Again, this is because the hole at x equals negative 2 does not affect our limit. So now, just as we've done previously, we're going to write our function, and we're going to plug in negative 2. So when we plug in x equals negative 2, we get negative 2 squared minus 2 times negative 2 plus 4. This gives us 4 plus 4 plus 4, which equals 12. So now we just need to write our answer in its final form now that we've got 12. So we'll write that the limit as x approaches negative 2 of x cubed plus 8 over x plus 2 is equal to 12. And again, this will be our final answer. So now for our final example, we're going to evaluate the limit as x approaches 2 of x minus 2 divided by the square root of x minus the square root of 2. So to do this, we're going to start out by first writing our function as we usually do, and then we're going to evaluate it at x equals 2. Doing so gives us 2 minus 2 divided by square root 2 minus square root 2. This gives us 0 over 0, so we have now shown, as is we need to do in step 2, that by direct evaluation we get an indeterminate. So now we're going to rewrite the function and we want to simplify it in some way. So here we see that in our denominator we have a radical. So what we're going to want to do to simplify an equation with a radical is we're going to want to multiply the numerator and the denominator by the radical's conjugate. So the conjugate of square root x minus square root 2 is going to be square root x plus square root 2. All we do is flip the sign between the two radicals. And what we're going to do that is now we're going to go back down here and multiply square root x plus square root 2 divided by square root x plus square root 2. In the numerator, we're just going to get the product of x minus 2 and square root x plus square root 2. And then in the denominator, what we'll get is x minus square root 2x plus square root 2x. And then we're going to get minus 2. We'll notice that our middle terms cancel, and we're left with x minus 2 times square root x plus square root 2 divided by x minus 2. Now, as we want to have happen, our x minus 2's cancel out, and we get that our initial function is equal to square root x plus square root 2, so long as x does not equal 2. So now, as we've done in the past two examples, we'll now say that the limit of our function, so the limit as x approaches 2 of x minus 2 over square root x minus square root 2, is equal to the limit as x approaches 2 of square root x plus square root 2. So now all we have to do is take our function, or take our new function, and evaluate it again when x equals 2. Doing so gives us square root 2 plus square root 2, which is equal to 2 square root 2. And that will be our final answer. So all that's left to do is now write it in the proper form. So we have the limit as x approaches 2 of x minus 2 divided by square root x minus square root 2 is equal to 2 radical 2. And that is our final answer. Okay, so with that being said, here are some additional practice questions for you to try on your own. They start with what to me was the easiest problem and get a little harder as you go along. So the answers to these 4 practice questions will appear in 5 seconds. So for the first question, you should have gotten 24. For the second question, you should have gotten 4. For the third, you should have gotten negative 4/5. And for the last one, you should have gotten 1/6. Next to these solutions, I've included what you had to do, or at least the starting procedure for all 4 of these questions. So the first one was again difference of 2 perfect squares, just where the x and the number was reversed from the example we did previously. The second one, you had to find the greatest common denominator and factor it out. For the third one, you had to factor both the numerator and the denominator polynomials, and doing so gave you a term that canceled out. And for the last question, it was again to use the conjugate. However, this time we needed to use the conjugate of the numerator because it was the numerator that had the radical. If you have any questions on these or any other questions about limits, feel free to leave them in the comments below, and have a good day. Thank you.